I'm Tom Fisher at the University of Minnesota. My colleague here is Peter Droege at the Liechtenstein Institute for Strategic Development. And we've been working with a team that includes also our colleague Guoping Huang, who's here from University of Southern California on this tool. Basically what we're going to do is we're going to do the first half hour looking at our work, going from local to global, and then the second half hour you'll hear from Carl Steinitz's team that are working sort of from the global to the local. And just a little bit of background, both of these teams really emerged out of the International Geodesign Collaboration, which is a network of universities around the world that actually had its start here at the Geodesign Summit. We first started talking about it in 2015. It actually began in 2018, and it really was an effort to connect mainly universities and nonprofits that were doing this kind of work around geodesign. Here's a map of the kind of range of membership, so you can see it's pretty diverse and extended, and has been sort of a group sharing ideas. The first several years of the work of this group was captured in this book that Carl and I and a colleague, Brian Orland, edited. So if you're interested in the work of the IGC, this is a terrific reference. We sort of went into abeyance during the COVID, and we came out of it with the commitment to start to work as a collective on global climate issues. And that's what we're really going to be talking to you today about. A lot of this is really looking at sort of world terrestrial ecosystems and the fact that our planet itself is very good at sequestering carbon if we let it, but the reality is that this is the planet that we have, which is one where, as you can see from this globe, there are a lot of spikes in carbon emission and methane emission, and so the global economy is having a deleterious effect on the health of the planet. And so our work that we're going to describe today is really about creating tools that allow designers, planners, decision makers to make better decisions in real time as a design tool in order to determine which of your decisions will have which impact on carbon accumulation, carbon emissions, or carbon sequestration. And so I'm going to turn it over to my colleague Peter, who's going to talk about the issues of climate that we're addressing here. So, Peter.
Thank you, and let me just say what a wonderful privilege it is to be here with Carl and Ryan and everyone. The entire mission, so to speak, that we are trying to pursue jointly with our friends at Esri. And when I was sitting out there in the sun at probably one of the most glorious days that I've experienced for a long time, I was thinking, what analogy is there to talk about that beauty? And I couldn't think of a better one than what those astronauts must have felt when they looked back at the planet in Apollo 17, and the oasis that Esri represents in the larger Los Angeles region is a bit like the planet Earth coming back to it. But what is extraordinary about that experience that's been expressed by one of the astronauts with, as we leave the moon, we leave as we came, and God willing, as we shall return, with peace and hope for all mankind, was felt again 54 years later. And here the quote from Victor Gloria is, "There's nothing that we cannot accomplish when we pull all of our difference together and work on something big for the good for everyone." And when you look at that second photograph, although it's an Earth that's slightly dimmer, with oceans that are slightly greener than 54 years ago, what you do see here is that bright arc that represents the atmosphere. In fact, that is, of course, the common we're all talking about. That's the common that we need to work on as our common good objective. But what did we do in those 54 years? We pumped 1.2 trillion tons of CO2 in the atmosphere. In fact, twice as much as was injected into the atmosphere since 1850 until 1972. And this is an extraordinary cognitive dissonance between the most extraordinary achievement, technological achievement, human achievement to reach orbit, to reach the moon, and this collective failure in taking care of that common, which we all share at this moment, the breathing of the atmosphere. And I think that thought I would like to keep here for a moment, and also remind you that the CO2 is a focus, but it's not our main focus. We're also focusing on other climate gases, and none is more dangerous at the moment than methane, rising dramatically 3 times in concentrations in that time period of these 2 missions. Now you can remind yourself of how many times we've seen ever hotter periods, ever new records being broken. But what we really should be asking ourselves, what do we do in our geodesign, in our GS community, to stop that ever-increasing record setting? And one thing we recently realized is that that heat escalation, which surprised most scientists, frankly, it happened 25 years earlier than hoped for, to breach 1.5 degrees in 2023. We now realize that, well, that's not it. That's only 1% of the actual energy injected into the biosphere, into the planet. The oceans absorbing 90% of the heat being absorbed by the planet. The land and the glaciers, the ice sphere, so to speak, absorb 9%. The atmosphere absorbs only 1% of that energy injection. And so recently, in the last 10 years, we've experienced a dramatic increase in that absorbed solar radiation. Now, that is not what's referred to as the actual climate effect, as that forced impact of heating, because you need to subtract the long wave radiation that is being ejected from the planet. That difference, that delta, is the climate forcing that we're talking about. But that has doubled in 20 years. And it's also very uneven across the planet where that occurs. If you look at the Northern Pacific and Northern Atlantic rectangle that you see there, and you analyze the radiation information that comes into the satellite, you see that difference, that delta between the absorbed radiation and the outgoing radiation, has been opening up dramatically in the last 20 years. So we've got the oceans kicking back that energy surplus, interacting with a slow disappearance of cloud formation over the oceans, interacting with aerosol reductions due to the sulfur emission reductions of ship traffic on the oceans. And so we've got a situation where there is this breaching of the planetary boundaries, and the CO2 concentrations and the radiative forcing being part of it, but it's, of course, an interaction that takes place with all the other indicators of the health of the planet, or what's being referred to by the Stockholm Resilience Center as the safe operating space. So the criteria, the coefficients, the indicators that exist before 1850. And so what they've mapped is various indications of health that have breached 80% of that level of health, so to speak. And one of them has been breached much faster than everyone expected, is ocean acidification. So I want to look at that very briefly, because it's probably something we need to calculate into our climate efforts, is that that reduction in the availability of calcium carbonate on the surface of the oceans is a dramatic indication of a decline of the health of the oceans. You see the baseline of 1850 in green there, the dropped availability of aragonite, which is calcium carbonate available to shellfish and other calcium-containing sea animals, and that drop much earlier than expected below what's defined as a boundary condition aragonite saturation state. Now, we used to define it more in terms of pH level, the current pH level of ocean, and the average is 8.05. 7.95 is generally regarded to be the level of no return of acidification. And so we are realizing now that the SSP, the shared socioeconomic pathways of 1 and 2 at the radiative forcing effect of 1.9 and 2.5 watts per square meter is what we need to retain in order to avoid a dramatic loss of ocean life due to acidification of the oceans. And there is this sort of very basic chemical formula where water and CO2 combine into carbonic acid and make carbonate ions unavailable to shellfish, and in fact break them up into 2 bicarbonate ions. Now, only recently, and it seems to me shocking to me that a paper was published that indicated that that analogy that we find in the oceans also exists in the atmosphere. As you increase CO2 in the atmosphere, what is the chemical effect of CO2 to animals that, yes, live in water, but also breathe the air? And we are part of that. And the question is not academic, because humans evolved largely over 1 million years, let's say, 1 to 2 million years. So we essentially are used to 800,000 years of a maximum of concentrations of 280 parts per million. Now, what happens if you increase that? It's currently 431 chemically. Well, the same thing happens. Our blood is going to try to cope with that chemically. People thought for a long time, we're just going to eject excess CO2, but the body doesn't work that way. It deals with it chemically in a rather unattractive fashion, that it begins to demineralize bone and deposit calcium in tissue, and maybe explaining some of the political events we've seen, reduce cognitive capability. As we approach 1,000 parts per million, that is long known, but these two researchers, Larcombe and Beerwith, 2 Australian respiratory scientists, measured the American population and discovered a reduction or an increase of 7% in bicarbonate ions in US population's blood. 7% increase in the last 20 years due to the fact that we're breathing too much CO2. So there is an immediate health risk, and they titled that paper, which rushed from a few hundred clicks in the first week to over 80,000 in the second week, with the atmosphere will be toxic within 50 years. Now, why hasn't anyone brought that up earlier? It seems to be so obvious that a carefully balanced chemical gas composition that's microbially and life-generated with these kinds of dramatic changes will have an impact back on the life that's there. So what are the focal points and targets in our efforts? We need to go back to 0-degree rise. In other words, we want to hold pre-industrial levels. We need to lower CO2 in the atmosphere by 35%. We have to act last week, 20 years ago, but no later than this year. And if we manage to bring our emissions, our fossil fuel industrial emissions, to 0 by, let's say, within 10 years, theoretically, we still have to remove at least 7 gigatons of CO2 for 50 years, assuming that the ecosystems that are helping us in that at a rate of about 20 gigatons a year don't deteriorate too badly in that period. And so that's a kind of a reference we are using for our local projects. We're putting our local projects into a national context based on per capita CO2 emissions that are available globally each year through the Global Carbon Project. And by doing so, we're able to sort of kind of rate our local performance against notional national performance against this objective of reducing what is currently an average of roughly 6 tons of CO2 equivalent per capita emissions around the world. Qatar has 90, Somalia has almost none, to about 1 ton per capita per year. And so that is a kind of a reference point against which we're rating our reference projects. And so the key triggers are known. It's the fossil energy, it's one, which is still dominant in most parts of the world. It's deforestation, which is still a major driver on the terrestrial ecosystems world. We have various kinds of indicators, a lot of it optimistic and encouraging, a lot of it not so much. We've got industrial agriculture, which is a little underappreciated as a major emissions driver, but also a sector of industry and business that's quite easy to improve in terms of soil performance, in terms of mixed agriculture and so forth. But one of the major, perhaps the greatest climate driver is the oceans, or the health of the oceans. And the pollution of oceans, besides overfishing and other pressures on the oceans, is the key to understanding the decline of ocean ecosystems, particularly on microorganisms level, phytoplankton, zooplankton, that is reducing the ocean's capability to manage carbon and produce oxygen dramatically. That reduction is about 1% a year. And so what are the responses? I mean, it's no rocket science. Renewable energy is key, but it's not just any renewable energy. It can't be biomass burned. It has to be so-called real renewable energy. It's carbon-free. It's available instantaneously while we're using it. It's got to be a stop to plastics into the oceans, industrial runoff, PFAS, soot pollution. That all demolishes the ocean's capability to manage CO2, particularly. It has to be a focus globally on regenerative agriculture and nature protection, whatever you want to call it, proforestation, even under changing ecosystems conditions. That continues to be the major terrestrial driver of carbon retentions. It's not afforestation, because it takes 30 to 40 years to have a tree be fully carbon retentive. It's important, of course, but stopping the loss of old growth forests. Now, if you take those four and look at the studies that underlie it, you have a notional opportunity to bring down the CO2 concentrations within, let's say, 150 to 100 years. Now, we've developed a set of climate domains, or what we call policies and actions around that. And here, 8 domains. These are not land use categories. These are not land cover categories. These are little worlds of how the climate interacts with changes in our way of dealing with space. There's scientific aspects of that interaction, but there's also the question of business and industry and finance that lie behind that. So yes, it resembles a kind of a land use set of categories, but it's actually what we call domains, in other words, worlds in which we find a series of policies, we could call them, or actions, but also vectors in which those actions act. So these actions have the impact of avoiding greenhouse gas emissions, of sequestering it, of replacing energy systems, and so forth. And here's some examples. Agriculture, crop rotation is a classic improvement, but it's also in the world of renewable energy, as you have a move from centralized energy systems to decentralized energy systems, the opportunity of integrating agriculture with renewable energy. That's called, here in this case, a integration of solar photovoltaics. We managed grazing area, which has an opportunity to improve both. We need to particularly ramp down very dramatically the methane, escaping methane from abandoned wells, but also gas production, and move towards renewables. We have to avoid deforestation. We quantified the impact of avoiding a decision made already. We need to look at planning processes that have made decisions to allow deforestation. When you counteract that, you have a credit due in terms of that carbon improvement. Forestation I mentioned. And there's a series of apex industries which are particularly productive in terms of, and known to be productive, and affordably so in terms of reducing their climate impact dramatically. We look at the settlement systems and besides the distributed performance of buildings in efficiency and so forth, there is various ways and actions and agendas that can be spatially defined and applied, and they are in fact applied as part of everyday business in communities. And we just added a modicum of quantification to that action. And so these actions are polygonal attributes or downloaded or imported from government or community sources. And they include transportation, not only on the surface, but also in the air, on water. And these kinds of interventions spatially help improve the climate impact or performance offered locally. Water systems are the seventh category, and they both lend themselves to avoiding the runoff of polluted water into rivers and lakes and onto the oceans, but also an opportunity to create efficiency measures for producing energy from that, for instance. But a major factor is really still the oceans. Only recently it was discovered that this dreadful technique of fishing, bottom trawling, which has been in practice since the 1850s around the world, is still very much practiced in Europe, I know for a fact, stirs up 1 gigaton of CO2 each year, just by not just ruining the ecosystems, but stirring up deposited carbon from the ocean floor. And it takes on the average about 3 years for a third of that CO2 to escape back into the atmosphere. So it's a carbon bomb. And again, it's shockingly surprising to me that it was discovered so late, that it's such a important fact that could have been researched much earlier. And then the protection of various ecosystems are part of that. Now, we've turned it into a kind of a wonderful world with the help of Goping and with the contribution of people at the University of Minnesota. We assisted in that too. And I think if I hand it back to you, you can close with some words on what do we do next.
Yeah, thank you, Peter. Yeah, so what we've done is develop tools that enable all of you to address the issues that Peter's been talking about in real time as a design tool. And so with a partnership with Esri and their experienced user team, we've developed this app that allows you to basically identify a geography that you're working in, to set the sort of the polygons and the geography of what you're planning to do, and it gives you then a series of over 150 climate actions that have coefficients tied to them. So every decision you make, it is giving you real time what is the carbon footprint of this decision versus that, and enables you to develop several scenarios and then evaluate those differences. And the idea of this is because you get immediate feedback, it can be a design tool, a decision-making tool. You don't have to wait for the answers. You can do it as it occurs. And these are just some examples of what the app looks like. This is available for free for anyone who wants to join the IGC, which is also for free. All you need to do is register, and you get access to this app and all of the climate actions that are part of the directory. And so again, we encourage you to do that. And what we've been doing is we've been piloting this. So we've been talking to the NDC partnership, the Nationally Determined Contributions Partnership, as part of the UN. Our goal is to get this in the hands of all 197 Paris Paris Accord countries to help them meet their carbon goals. The NDC partnership has been promoting this app, and we are planning to develop a kind of toolkit so that every NDC partner can have the tools they need to achieve their goals. And I'll just go through some of what we're currently doing. We have a series of countries and universities now utilizing the app, and that includes Nigeria is doing their two studies in Nigeria, one in Lagos and one at the desert edge. There's a team in Jordan that's looking at water, both drought as well as flooding at the same time. There's a group in Panama that is looking at itself as a kind of green haven, and they're also concerned about drops in the water levels of the Panama Canal. And then here's the other Nigerian team, which is looking at desertification. And so, this is what we want as many people to be using as possible. The idea here is that the Climate Action Directory that LISD has developed and the tools that we've developed and the Experience Builder app that we've developed in partnership with Esri is really to be used to make change. And so here's another project going on in Thailand around in Bangkok. And so the competition is underway. We're going to have the review of this first round in June. The winners are going to be at the user conference in July, and we plan to do it again. So if you're interested in taking part in this competition, again, it's free, and we would welcome all of your participation. Thank you.